Hello, we're going to do some Green's theorem problems. So here is the integral. It's a line integral. And this is our vector field. You can take a minute on your own to see that there's no way that this is a gradient for a little f. You can check the partials yourself. So the fundamental theorem of line integrals does not apply. Here's our curve, and it's a simple closed curve. It's just a circle, radius 2, and it's oriented counterclockwise. So we're doing a work integral. How much work does it take to go around this circle once in this vector field? And that's our problem. So let's try it as if we don't have Green's theorem. Let's try it as a line integral. Fundamental theorem of line integrals doesn't apply because we don't have an easy gradient. We don't have a gradient function at all for this. This f is not the gradient of a scalar function, little f. So I'm going to have to do what you're supposed to do if you got no other choices and it's a line integral, which is substitute like a maniac. Remember? Substitute like a maniac. And what do you substitute for? Well, here's f, and f is a function, a vector field of x and y, and here's x and y. So, and then it's a dot with dr. Well, that's the dot with the derivative, so it's taking care of the dy and the dx. So one of the ways you can write this thing is you can write it as, okay, so it's going to be x, which is 2 cosine t, comma, x minus y, 2 cosine t minus sine t, 2 sine t. That is dotted with, the derivatives of r. So that's going to be dotted with, boy, can I fit that in here? Looks like I'm running out of space. I'm going to see if I can squeeze this in. I'm dotting it with the derivatives. So the derivative of 2 cosine t is negative 2 sine t. And the derivative of 2 sine t is 2 cosine t. And I throw dt on the end. Can we get this all in the picture? I'm going to step to the side here and hope that you can get all that. But just rewriting it all. So this is our problem. Just rewriting everything. So I'm going to have 2 cosine t dotted with negative 2 sine t. So it's negative 4. Oh, sorry. This is from 0 to 2 pi, obviously. 0 to 2 pi. So negative 4 cosine t sine t. And then that's plus 2 cosine t times 2 cosine t. So that's 4 cosine squared t. And then negative 2 sine t times 2 cosine t. So it's negative 4 sine t cosine t. All of that dt. So that fits on the board. We got that going. Now, I can see I got negative 4 of these and negative 4 more, so that's negative 8. I'm going to do this simplification here. Save a little space. All right. Now, I happen to know a few tricks for these integrals here. This guy here, this is the same as negative 4 times sine of 2t. So I have integral 0 to 2 pi, negative 4 sine 2t dt. And this piece here, I've got a plus 4, but it's cosine squared. My formula for cosine squared is going to be 0 to 2 pi, and that's 1 plus cosine 2t over 2 dt. And remember that formula for cosine squared. There's a formula for cosine squared and a formula for sine squared. This is one for cosine squared. Now, I'm going to use my brain. This thing is 0 because it's 2 cycles of sine from 0 to 2 pi. That all cancels out. That's a big 0. Then I don't have to do this integral. Over here, I've got 2 cycles of cosine from 0 to 2 pi. That goes to 0. So my final part, the only part I have to integrate is that 4. I'm going to have a 1/2 and I'm going to have a dt. Well, that's a t evaluated from 0 to 2. So I'm going to have a 4 times a half times a 2. So that's a 4. That's my answer. Well, that worked for a 4. Now let's try and see, sorry, 2 pi, 2 pi. That's a 4 pi. Thank you. 4 pi, 4 pi. And that's the correct answer. Now we're going to do it with Green's theorem because we have Green's theorem. We haven't proved it yet. That'll be on my next video. I just didn't feel like doing a proof tonight. Did you feel like doing a proof? I don't feel like doing a proof. The Green's theorem proof is actually quite beautiful. And we're going to look at that another day. All right, now we're going to do this instead of as a line integral, we're going to do it as Green's theorem. I'd like to rewrite this integral and see if it's shorter. That wasn't too bad. That was just a line integral, and it wasn't too bad. But look at how smart we were. We saved a lot of work with those zeros. Now, as a Green's theorem problem, I have to recognize that this guy right here, that is P, and this is Q. So this integral, this thing that we're trying to do, is going to be the double integral over the domain. That's that circular domain there. Only this time, it's the disk. D is this part. So, do you know what we're going to have to do? If we want to do this with Green's theorem, we're going to have to go into polar coordinates because it's a two-dimensional domain, it's a circular region, and I do not feel like playing with all those square roots. But I do get a nice integrand. My integrand, if you remember, is supposed to be q, partial of q with respect to x minus the partial of p with respect to y. So partial of q with respect to x is a 1. Partial of p with respect to y is a 0. Let's just say dy dx here. Let's just say that. Well, look at, what is this thing? What's this the integral for? Your integrand is a 1. You're integrating over a circular region. This is the area integral. Area of the domain. It's just the area of the domain. Well, the domain is a circle of radius 2. Well, a circle of radius 2 is pi r squared. Pi times 4. 4 pi is my answer this way. So I don't even have to do this integral this way. With Green's theorem, I see what it is, and I don't have to do it. Now, if you want to do the substitutions, be my guest. It's actually quite easy. We'd have to do this. You have to have an r in there because you're switching over. Dr d theta. So there's your Jacobian for switching over to polar. And you're going to go, r goes 0 to 2. Theta goes 0 to 2 pi. And you're going to do r squared over 2 evaluated from 0 to 2 times theta evaluated from 0 to 2 pi. So I'm going to have 2 into r squared. 2 goes in, and I get 4. Divided by 2 is 2. 2 times 2 pi. 4 pi. I got it doing it the long way. So in a sense, we did this problem 3 ways. One with geometry, but it's inside of Green's theorem, and then Green's theorem doing it out by all the way out with the polar. So that's what it's like doing one of these things. Let's do one more Green's theorem problem. This time I'm going to kind of cheat on you here because it's an integral that I can do by hand the long way, but it takes a long way. I can check the integral on the computer, and I get the same answer, so I'm pretty sure I have the answer right. But I wanted to do a problem that was a little bit more typical problem where Green's really pays off, or so it's really worth doing it with Green's theorem. So it's a new integral to try. I'm going to do this one. I'm going to do the integral over c of cosine y dx plus 2y minus x sine y dy. And we happen to know that, let's see. Well, this is not a Green's theorem. This is a fundamental fundamental theorem of line integrals. All right, so here's my c. My c is this. It's the line y equals 1 minus x over 2, but I parameterized it with t and 1 minus t over 2, and t goes from 0 to 2. So that's my c. I want to do this line integral, and I'm just doing this, the 0 to 2 thing. Now, you can do this one all the way out, but one of the computer algebra system says the answer is 1. So I've got the right, that's the right answer. You can do it all out. You can do this by line integral means. It takes up half a page. It's not a killer. But let's do this one with the fundamental theorem of line integrals, because this is my P, this is my Q. So I'm not doing Green's theorem, but I'm checking Q sub x. Q sub x is negative sine y. And P sub y, negative sine y. So there exists a function whose gradient is this. You know, the cosine y comma 2y minus x sine y. So what would that function be? Well, we did that part in class where you have to run off to the side. Okay, run off to the side and solve this integral. You actually do cosine y dx. You actually do the integral 2y minus sine y dy. You actually do these integrals. I'm going to skip that part. You guys should do this. But what you're supposed to get is little f of xy turns out to be x cosine y plus y squared. So you can see if I take the partial of this with respect to x, I get her. Take the partial of x with respect, partial of this with respect to x, you're going to get cosine y. There it is. Take the partial of this with respect to y, you'll get negative x sine y. There it is. And 2y. There it is. So I've got the right thing. You guys should practice with that. I'm not going to do that for you. But now that I have that little f, I think I can fit my answer right here. I think I can fit the answer right there, because what am I supposed to do? I'm supposed to just evaluate this function at the endpoints of this thing. All I need are the endpoints. So I'm going to find those endpoints, and I have to have the second endpoint being evaluated first, and then the subtraction sign. Oh, such a good weasel. Such a good weasel. So this is Cocoa Bananas. She doesn't know that you're looking at her. She doesn't know anything. Now, I'm going to pop in, I need these ordered pairs. When t is 2, I get a 2, comma, 0. So it's going to be f of 2, 0 minus f of, I'm going to pop in a 0, and that gives me 0, comma 1. So it's f of 2, 0. F of 2, 0. Well, cosine of 0 is 1. So I have 2 times 1 plus 0. So that's 2 times 1 minus, now I'm putting in 0 for x, that's a 0, and a 1 for y, that's a 1. 2 minus 1 is 1. 2 minus 1 is 1. Didn't need a calculator for that one, but it matches the computer algebra system version. Or if you want to do this one the long way yourself, it works. You just have to go a ways. There's an integration by parts in there for you. Just a little Thanksgiving treat for you. That was a good video. Talk to you later, kids.